Is the chapter where we are focusing on organohalides, also known as alkyl halides. Alkyl halides slash organohalides are compounds that are generally represented as RX. What does R mean? Anybody?
Organic group.
Something or exactly, and X is the halogen covalently linked to the carbon. So when we have an sp3 hybridized carbon covalently bonded to a halogen, that is an organohalide or an alkyl halide. And you've seen those before actually. The part of this is review because we've done this last quarter, so hopefully it will come back. Okay, so how do we name organohalides? Nomenclature for organohalides, naming of organohalides. Now there are two different ways in which most compounds can be named. One of those ways is a common naming system. Common naming system was used before a more systematic IUPAC naming system came into place. So in the common naming system, organohalides are called alkyl halides. Two words. So for example, so whatever the R portion is, followed by whatever the halogen is. So for example, if we had, I'm going here, if we had, for example, so what is the R portion called, anybody?
Propyl.
Exactly, right? Prop, because there are 3 carbons, il, because it's a group, and then what's the halogen?
Iodide.
As a separate word, iodide. Propyl iodide. Right? Make sense, everybody?
Mm-hmm.
So, what do you think you would call this guy? Oh, you're taking notes as well. Are you an OChem student?
I took OChem kind of already.
Oh, so you're going to help her.
Sure.
Perfect. Yes. What would we call this guy? So what's the R part?
Phenyl
Phenyl?
bromide.
Exactly. Phenyl bromide. Agreed? So the alkyl part followed by a separate word, halide, whatever the halide is. Does that make sense, everybody? Mm-hmm. Yes? How about
So,
just using the common system?
Okay.
The common system. So what would we call this in the common system?
Benzyl chloride.
Do you all agree?
Yeah.
That's benzyl chloride. Everybody okay?
Mm-hmm.
How about this one? Terbutyl bromide. Everybody okay?
Yeah.
Terbutyl bromide. How about here?
Isopropyl iodide.
Perfect. So whatever the R is, followed by the halide. Everyone okay?
Yes.
Benzyl chloride, terbutyl bromide, isopropyl iodide. So that works for simple ones. If it were a complicated one, for example, I'm just making something up right now. Then this method doesn't work. Common naming system is can be used for simple things. When the molecules become complicated, the common naming system does not work. That's when IUPAC system comes in. Now this we've done before last quarter. So can somebody tell me what would be the IUPAC name for this guy?
3-chloro, 5-isopropyl.
Are you sure?
No, because two
First is to
One.
find the parent chain, the longest continuous chain.
dimethyl.
Yeah, go ahead. What were you saying, Mark?
1,2-dimethyl.
You have to start from here, then number the parent chain.
Oh yeah, 2,3-dimethyl 5-chloro.
But which comes first? Alphabetically.
Yeah.
Groups are labeled alphabetically. So dimethyl or chloro?
3-chloro.
5-chloro. 5-chloro.
5-chloro.
5-chloro.
2,3-dimethyl.
dimethyl. Does di count?
No.
And?
Heptane.
Exactly. We've done this last quarter. Everybody okay? Right? So first step, find the parent. Second step, number the carbons in the parent to get the smallest combination of numbers. And then third, label or rather list the groups in alphabetical order followed by the parent. Yes, Karen?
I think I forgot.
Go ahead.
Why does the one start?
Not from there?
Yes.
Okay, let's give it a try.
I was gonna ask that too.
Let's say I numbered it this way. What would be the number for chloro's position?
3.
What would be the position numbers here?
5, 6.
Which combination is smaller?
5
5
plus
to
2
3 or 3
is 10.
by
Plus
6?
5 is 8. 3 plus 5
Right?
plus 6 is 14.
5 plus 2, 5, that's 10. That's what?
14.
Which is, so always go for, first rule is, go for the smallest combination. So in this case, the smallest combination is the red one. Make sense, everybody? We've done that last quarter. Is that coming back?
Yep.
Cool. Now, IUPAC naming system can be used for any. It can also be used for the simple ones. So can someone tell me what would be the IUPAC name for propyliodide?
Iodopropane.
So I think we need to be in iodopropane case, we need to be a little bit more specific.
One.
One iodo, because the iodo can be on 2 as well, which will be different. Propane, yeah. Okay, what would you call phenylbromide? Oh, we haven't done this yet, so let it be. We'll get to it later. How about benzyl chloride? What would be the IUPAC name for benzyl chloride?
1-chloro 2. No, phenyl. No.
Where's the 2?
No, yeah, you're right.
Would it be one chloral, one benzyl?
Benzyl.
Not benzyl, phenyl.
Phenyl. And then what's the parent? Okay, so you're saying 1 chloro, 1 phenyl, so what's the parent?
Oh, cyclo, not
That's benzene, that's not cyclo anything.
It's
Oh.
butane.
Butane, where's the butane?
No.
Ethane.
It doesn't have 4 carbons.
No, it's not. Wait.
What's your parent? What's,
Is
there's
it
no hexane here.
ethane? Is
There's
it
no, where's the ethane? Show it to me.
Methane.
methane?
The parent is simply the methane, the carbon the only carbon that's not part of the benzene ring. So, what would be the IUPAC name for benzyl chloride? I'm ready.
One
One.
phenyl.
C comes before P.
1 chloro.
Oh, 1 phenyl, 1 chloro. Okay. Chloromethyl. Oh.
Right? Everybody? Okay? Okay, what would be the IUPAC name for terbutyl bromide? No, I'm not erasing that. Just making space here. What would be the IUPAC name for this guy? What's the parent? Start with the parent. The parent has to be the longest continuous chain of carbon atoms.
So Heather?
1, 2, 3.
Yeah.
2.
So what's the parent?
Ethane.
Propane.
No, it's
Propane.
Propane.
oh, that's right, yeah.
2 bromo
Yeah.
methylpropane.
I think what's happening right now is we've forgotten.
No, it's that.
Yeah, I forgot.
I didn't forget that. It's just
That's okay. Some are forgetting.
I'm trying to separate them. That's all. That's the thing I'm doing, which is wrong.
Right?
Yes.
Yep.
So what should it be called? What should this guy be called?
2-bromo-2-methylpropane.
2-methyl.
Okay, next one.
2-iodopropane.
Do you all agree? 2-iodopropane? Everybody okay? The parent? Everyone okay?
Yep.
Okay, cool. Let's do a few more. Let's IUPAC right now. Let me draw a few more structures. I need you to give me their IUPAC names.
One,
I'm not done.
3, 4, 5, 6.
Ready? Okay, so let's look at the first one. What is the parent?
Isn't it 9?
9.
No, 9.
I'm assuming is it 1, 2, 3, 4, 5, 6, 7, 8?
Octane.
Octane, right?
Oh,
Yes.
it is octane. Why did I do that?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I right?
Yes.
So is it octane?
Yes. It's an octane.
Where should we start numbering the parent from? This end or that end?
The left.
This end?
Yes.
Oh, because
Okay,
there's that
1,
chloro.
2, 3, 4. Are you sure?
Yes.
6, 7, 8. Okay, we can explore both options and then decide what's the better
1, 4,
option.
6.
Okay. Are you ready to tell me the name?
Yes.
Okay, go ahead.
4 bromo,
4
1
bromo. Uh-huh.
comma 6 dichlorooctane.
Sorry, what was that?
1 comma 6 dichlorooctane.
We missed something.
4, 5, 9.
Oh, I forgot the.
I did the same thing.
The ethyls, right?
Yeah, the alphas. So before 5 di
Oops, excuse me. 5. And then octane, right? What if we numbered from the other end because we were considering? Let's see. So 1, 2, 3, 4, 5, 6, 7, 8. So what would that be? This would be 5, right? These will be 3, 8. Am I doing that right? And these will already lost, right? So it's already much
5 plus
higher.
3 is 8 plus 8 is 16. Plus
Does
4 is
everybody
7 plus
agree?
5 is 25.
Is everybody okay?
Yes.
Cool. Next one.
Trans 1 bromo.
So
3.
I would not do trans with that. Yes, it is because, but there can be two different transes, right? They'll be enantiomers of each other. If wedges and dashes are shown, no, it's not cis. If wedges and dashes, I can do this. If wedges and dashes are shown, what would be a better way of indicating stereochemistry? Exactly.
RMS.
Exactly. Because when it comes to trans, isn't its enantiomer also trans?
Oh yeah, it's also trans.
So when you are saying trans, you're not specifying which enantiomer.
Oh.
But when you're saying RRS, then you're specifying, okay, it's this one, not that one. Does that make sense?
Yes.
So if wedges and dashes are shown, RS is the better way of indicating stereochemistry. So let's use that. Do you remember RRS?
Yes.
So everything we learned in 261 is going to be used now. Those were tools that we will now use constantly. Okay, so what's the parent?
The cycloheptane.
Cycloheptane.
The
Right.
cycloheptane.
Where would you start numbering the cycloheptane from?
1 bromo
You
3
agree?
methyl.
From the bromo side?
Yes.
Yeah, so, and go clockwise in this case?
Yes.
Okay, good. And now RRS. So is 1 RRS? Anybody? So that's priority 1. 4 is already back. 1, 2, 3. This is R. Am I right? Everybody okay?
Yeah.
Everybody good? Okay, what about this? Oh, H is pointed towards me, so I should remember to flip. Okay, fine. 1, 2, 3. So that's R as well. Am I right? Did I do that correctly?
Yeah.
Please, anybody? Is everybody remembering this from last quarter?
Yes.
Cool. So now we're ready to name. So can somebody tell me what is the name? What do we start with?
The 1R,
Comma,
3R.
3R. Start with the stereochemistry.
Mm-hmm.
Now the rest, okay?
1,
1 free R 1 bromo free methyl cycloheptane.
Perfect.
heptane.
Is everybody remembering this? Everybody okay? Now to the next one, can we do R or S?
Yes. No.
The next one we can't because there are no wedges or dashes shown. But can we do cis or trans?
Yes.
Yes. So please go ahead, tell me what would that be called?
Trans 1 chlorofree ethyl cyclohexane.
Trans. By the way, the T of the trans and the C of the cis are lowercase. They're always lowercase, even if they're at the start of the sentence. They're never uppercase. These are prefixes that are always lowercase. Trans, what did you say, Carter? 1 what?
1 chloro free ethyl cyclohexane.
Yes.
Is everybody agrees with that?
Wait,
And is everyone okay with, yeah, go ahead.
just a bit,
Yeah.
so isopropyl, the I counts, right?
Yes, and cyclo counts.
And then for terbutyl, does the T count? No?
It doesn't.
Okay.
On the only two prefixes that count for for alphabetization is iso and cyclo.
Okay, thank you.
Everything else doesn't count.
Everybody okay?
Yes.
How about the last one? Please go ahead, tell me what would be the IUPAC name for the last one.
2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7.
What's the parent?
Heptane.
Heptane.
Okay, so should we number 1, 2, 3, 4, 5, 6, 7, or should we number 1, 2, 3, 4, 5, 6, 7?
Blue.
Blue?
Yeah.
Does everybody agree that the
1,
blue
3,
will give
6.
us a smaller combination of position numbers?
2, 2, 3, 6.
Okay.
2, 2, 3, 6.
Okay, so go ahead, tell me the name then. Can we do RS?
No, we can't.
There are no stereochemistries shown, although there are 2 stereo centers, but they didn't tell us what they
2-dimethyl.
2. Say that one more time.
2-dimethyl.
But shouldn't something else come first?
Benzyl.
Benzyl comes first, right?
Oh, yeah, sorry.
Alphabetical.
Yeah, okay, yeah.
3,
So
benzyl.
3 benzyl. Uh-huh. What comes next?
6 bromo.
Uh-huh.
And then the 2 dimethyl.
2 dimethyl. And the parent? Heptane.
Mm-hmm.
Does everybody agree? Questions? So we've already done this last quarter, but is it coming back?
Yes.
Cool. Is that? Okay, let's talk about how do we make alkyl or organohalides? How do we make them? Where do we get them from? There are different families of compounds we can get alkyl halides from. Alkyl halides industrially are created from what family is this? Anybody? If I have this is an alkyl halide, right?
Yeah.
But instead of the X, if I put an H, what does it become?
Carbo.
It's a
Family.
it's
Okay.
a methine.
Met.
Oh, I forgot. Okay.
It's a methine.
There we go. Don't make it more complicated than it's supposed to be.
It's an alkane.
It's an alkane. Alkane. An alkane can be converted into an alkyl halide. Can somebody tell me what kind of reaction is this? Remember the 4 big categories of OChem reactions. It's a substitution reaction. What has been substituted here?
A
H has been replaced by
an
the
halogen.
Exactly. And this is the reaction we will study in detail in this chapter. In chapter 10, we will go look at it, this reaction in detail, the mechanism and how and why and blah, 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 blah. So that is one of the ways of making an alkyl halide. Another way of making an alkyl halide is actually 2 others, I would say. One is from an alkene and another is from an alcohol. Both of these we will explore, both of these actually we will explore more in chapter 11. So we'll save it for them. But just as an introduction, that alkenes can also be converted into alkyl halides. Alcohols are also a very good source of making alkyl halides. But in chapter 10, in this chapter, we are focusing on only one of the ways of making an alkyl halide, and that is from an alkane. We good, everybody?
Mm-hmm.
Okay, so alkanes can be converted into alkyl halides basically by substituting a hydrogen with a halogen. Now I want to write this equation a little bit differently because this carbon has to be what? Has to be sp3. It's the hydrogen on an sp3 hybridized carbon which is replaced by a halogen. Not sp2, not sp. So substituting a hydrogen on an sp3 hybridized carbon by a halogen. What is used for this reaction? What are the reagents used? The reagents used are basically halogen gas. And the ones that are typically used for this reaction are chlorine gas or bromine gas. Iodine, the reaction is way too slow to be productive. The rate of the reaction is way too slow. And fluorination is extremely high that it is dangerous. So not use. Exactly, it's exothermic. Using fluorine creates a lot of energy. Dangerous, not useful. Iodination is highly endothermic. It takes so much energy that it's not useful, practically speaking. So practically speaking, this reaction is best when you're either chlorinating it, meaning you're putting a chlorine on it, or you're brominating an alkane, putting a bromine on the alkane. But not by itself. The way I've written this equation, it won't go anywhere. This reaction will only happen if I use an energy source. Now please note the symbolism here. The energy source that is required for this reaction can either come from heat. That's our indication of heat. So don't look at it as delta like delta H and delta S change in H. No. What we are saying basically is heat. We are heating it. Or light, H nu. That's not V, when V is velocity. That is nu, which is, what is nu? Planck's constant times frequency. That's the energy of electromagnetic radiation. So the energy is either coming from heat or coming from light. Everybody okay? So these two symbols, please get used to seeing them. Because we do sometimes see them for different places, at different places you will come across them. So whenever you see this, read it as heat. Whenever you see this, read it as light. So energy has to be provided for this reaction to take place. Energy has to be provided either in the form of heat or in the form of light. Everybody okay? Let's look at examples, then we'll get into the mechanism. How is this happening? What is going on step by step in order for the products to be created? And then we look at other details of this reaction. So we'll start small. Let's start with, let's start with methane. The smallest alkane possible, methane. So methane, if it is chlorinated, meaning I'm using chlorine gas with light, it's undergoing substitution reaction. Can somebody tell me what would be the product? Don't think too hard, go with your gut.
CH3Cl.
Right? Everybody agrees? It's the hydrogen on an sp3 hybridized carbon that is replaced by the halogen. The hydrogen is being substituted. What's the byproduct, anybody? Louder?
HCl.
HCl, exactly.
Plus HCl.
That's the byproduct. Side product, some people call it byproduct, some people call it side product, whatever you want to call it. It's also created. Everybody okay? Mm-hmm. Okay, now, this reaction actually goes through free radical mechanism. Did we look at free radicals briefly last quarter? Right?
Oh,
yeah, I think we did in the chapter 6, but very briefly. We didn't go into details, just very brief. So what are free radicals? Can somebody remind me? What's a free radical? So a free radical, basically, anything that has anything that has an unpaired electron is basically a free radical. Now, in some cases, FII, how many electrons does hydrogen atom have? One. It's a free radical. If you think about it, it's a free radical because it has a single electron which doesn't have a partner. Isn't that right? So hydrogen atom is a free radical, really. Is it charged? Is there any positive or negative charge on it?
No.
It's neutral. All free radicals are neutral. All free radicals end up having no charge because they don't have extra electrons or fewer electrons. How about chlorine? How many valence electrons does chlorine atom have?
7.
So notice 6 of them are paired, but there's one unpaired electron. It's a radical. Isn't that right? Anything that has an unpaired electron is a free radical.
So like nitrogen.
Nitrogen can also be, absolutely. If it is existing as a single, absolutely. Absolutely. Anything that has an unpaired electron is a free radical. Now, free radicals are highly reactive. They are extremely reactive. And that's why, health-wise, if you think about health-wise, we want to stay away from free radicals because they are extremely they're very unstable, which means they want to react very, very quickly and pair up with something so they don't have that single electron. So radicals are extremely reactive as well. So this reaction goes through a free radical mechanism. Now, before we write the mechanism and all, let's just review something we did briefly talk about last quarter. If I have methane and I'm breaking one of the CH bonds, let's say, to make a methyl free radical. So I'm breaking this bond to make that free radical. By the way, what else should also be produced along with that, just to help us understand? Hydrogen free radical, also aka hydrogen atom, right? Same thing. But my question to you is, before we get into the mechanistic details, in what manner must this bond break to create those two neutral species, free radical species? Louder?
Arrows?
What kind of arrows though?
Curved arrows?
Okay, what kind of curved arrows?
What
Single-headed curved
single-headed.
arrows. What do we call those processes that involve a single electron transfer? Hetero is 2
Homolytic.
electrons. This is homolytic bond breaking. Exactly. Heterolytic processes where 2 electrons go here and 2 electrons go there will always result in ions, plus or minus, or use ions. Homolytic bond processes, whether it's bond making or bond breaking, will either create radicals or use radicals. 1 electron in this bond went to the hydrogen, the other one went to the carbon. You guys agree?
Mm-hmm.
So what do you think will happen if, again, it has nothing to do with that reaction, we're just trying to remember things we did last quarter. What if I have a chlorine atom, chlorine radical, of course there are other electrons too, but we don't care, I have a T-butyl radical, and they both have unpaired electrons, but the electrons come together. Now notice single-headed curved arrows, but can someone tell me what will be the outcome of this process? So when the electron from chlorine pairs up with the electron from carbon, what would be the outcome? What would be the consequence of that? The result.
T-butylchloride.
Louder?
T-butylchloride.
Exactly. That is going to create a covalent bond between carbon and chlorine. Do you guys remember us talking about these curved arrows? We did it briefly, I
Yes.
agree, but we did talk about them a little bit. So this is a homolytic bond breaking, splits evenly, creates radicals, or homolytic bond making, where both parts bring one electron to create a bond. Yes.
This might be a little random off topic, but to break that CH bond, wouldn't it have to be something?
You need
strong?
energy.
Right, so it would be like heating something
Heat
up.
or light, exactly. This is the energy needed to homolytically break a covalent bond is called bond dissociation energy. And every single covalent bond has its own bond dissociation energy, needs a certain amount of energy. CH needs certain amount, CCl might need a different amount, blah, 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 blah. You got to provide that energy, exactly. This is an exothermic process. This is an endothermic process, absolutely. And that energy is why we need the heat or light. Because unless you can provide that, we can't start the process.
Yeah.
But everybody remembers this formalism? Are we okay? Yes? Okay. So with that knowledge, let's look at closely with the mechanism, the free radical mechanism where methane is getting chlorinated. Now, please note, free radical mechanisms are written in a very specific manner. Free radical mechanisms must show three very distinct stages. And when you write it, you have to write them in, here's the first stage, here's the second stage, here's the third stage. The first stage, when you're starting the process, you took the reactants, put the energy source in, and now we are starting it, is called the initiation stage. Once the process has been initiated, you know that like the spark plug, the spark in your car engine. Once again, I don't know too much if I say something like that's not how it happens. Just forgive me, but the way I see it, you know, the spark plug creates a spark, which creates the combustion going with the gasoline. Is that right? Am I kind of sort of right? Right. So this is your spark. It starts the process. Once the process starts, it gets into the second stage, which is the most important stage. Actually, I'm going to go to the next board because I need more space. It's the propagation stage. You don't have to write it just now. You can write it in order so you don't mess up the format and all. And once the propagation stage is all over, it gets into what is called the termination stage. So three very specific and distinct stages in which this reaction happens. So let's look at initiation. In initiation stage, as the name suggests, is where the whole thing starts. So in this reaction, in the initiation stage, actually I don't need the number, it's the halogen, in our case, it's chlorine, Cl2. Using the heat source that we provided, what did I use? I used light here, so the heat source causes the bond to dissociate, homolytically break. We need that energy. Can someone tell me what will be the outcome of that process?
2 free radicals.
To which free radicals?
Cl point,
Exactly.
Cl point.
Do you guys agree? In this reaction, that's the initiation stage. The halogen breaks apart homolytically, creates halogen free radicals. Now, do you expect this stage to be exothermic or endothermic?
Exothermic.
So, absolutely. In this stage, bonds only broken, right? And it is an did you say exothermic? Sorry,
Yeah.
Are you sure? We're breaking a bond. If we're breaking a bond, should we take energy, give energy, or does it absorb energy to break the bond, or does it release energy to break the bond?
Endothermic.
Did I say it the opposite in the early. Oh shoot, sorry. I think that's why you got confused to Carter. No, let me straighten it. I think I mixed those up earlier. Bond breaking is endothermic. It takes energy. You need to provide energy to break a bond. Bond making gives energy. That's exothermic. So here, since we are only breaking a bond, that's an endothermic process. Are we good, everybody? That is the reason why if you don't have the energy source, nothing happens, because you can't do this. Yes? Okay. Now come to the propagation stage, the most important stage in the whole process. Now there are some very important points that must be met when you write the mechanism for the propagation stage. First thing that you will notice is that every step in this stage has bond breaking, although of course everything has to be homolytic, and bond making. Oh shoot, I didn't leave space for myself. Why do I do this? Okay, I'll write it here. That is very, very important. Every step should show some bonds being broken while some bonds being created. Next thing that is very, very important in this stage, which must be demonstrated, that the sum of all steps must equal the overall reaction equation. If that's not happening, something's wrong. Our overall, remember in this example, this is our overall reaction equation, right? So when we write the steps in the propagation step and you add all those steps up, it should equal that. Otherwise, something's wrong.
Mhm.
And finally, which also must be demonstrated in the propagation stage is, do you guys know what is a chain reaction? Do you know, what does that mean?
One after another.
What does that mean?
Like some products.
Which affects this, which, right? It just keeps going and going and going and going.
Something affects.
That's
this.
very typical of free radical reactions. That's why once a free radical reaction starts, it's very hard to control it, because one step creates something that goes in the next step, which creates something that takes it back into the first step, which goes back, and so it just keeps going and going and going, and you can't stop it. You cannot stop it. That must be shown in the propagation step. All steps must indicate otherwise something's wrong. We good, everybody? Those are three very important characteristics of the propagation stage. So, in this example, how would that happen? In this example, there are two steps in the propagation stage. I'm talking about propagation stage. Once we got the chlorine radical, the chlorine atom from initiation stage, it reacts with one molecule of methane. In this manner, please notice the arrows. That electron pairs up with this electron, and the other electron goes to carbon. So, can someone tell me, are these two curved arrows going to cause a bond making or bond breaking?
Making.
Do you guys agree? What about these two curved
Breaking.
arrows?
Breaking about.
Every step has to show both. Can someone tell me what's the outcome when that happens? What does it create?
HCl.
HCl and
H3.
HCl plus CH.
there's no Cl.
Oh,
Cl went here.
H3. CH3, sorry.
CH3 what?
Cl.
No, Cl went to the hydrogen. There's only one Cl.
With the free radical.
Oh,
Right now there is only
CH3
that.
free radical.
Free radical. Oh, that's something. Oh shoot, I forgot one more. Can I add one more?
Yes, you can.
Every step must. Please notice my use of the word must, because that's important. Must use a radical and create a radical. Step number 1, bond broken, bond formed. And radical used, radical created. You guys see that? Everybody? Okay, that's step 1. What's step 2 of this propagation stage? The radical that we created in the previous step, methyl radical, now reacts with another molecule of chlorine. Again, please notice my curved arrows. This electron pairs up with that. Is that bond making, bond breaking?
Making.
And then the other electron goes there. What is that doing? Bond breaking, bond making?
Making.
What's
breaking.
that going to create?
A free radical form.
Exactly. It's going to create, of course, the chloromethane, no doubt, but it is also going to create, right? Every step must show bond breaking, bond making. Do you agree? Every step must use a radical, must create a radical as well. Do you agree?
Yep.
Now let's look at this one. Sum of all steps. When I take these 2 steps and add them, what's the sum? Anybody? This gets cancelled, right?
Yep. The CH free radical
gets
gets canceled too.
So what does that leave us with? CH4
Yep.
plus Cl2 produces CH3Cl plus. That's your overall reaction. Agreed? Everybody? Do you all see that? Very important. What about this requirement, the third bullet point? All steps must indicate that chain reaction characteristic that all free radical reactions experience. Do you think these 2 steps will create a chain reaction? Notice the first step is creating this, which goes in the second step, creates that, which goes back, creates this again, which then comes here, creates that again. It just keeps on and on and on and on till one of the ingredients gets used up. That's when the reaction will stop. We cannot control it. Free radical reactions, that's why are health hazard, because once it kickstarts, we can't control it. It goes on and on and on and on. Yes.
So what would this look like in a solution? Would it be
Good.
boiling?
So well, that depends on what your alkane is. Depends on how much heat they need in order for it to go. But you will do some of this in lab. I think the second lab you're doing this a little bit. Some of them need more heat. Others can happen with just room temperature and room reaction, ambient light, enough to get started, and we can't. That's why some substances you need to store very, very carefully so that they don't go through this.
Like you can't see it. I think what's happening in my brain is I think of halogen, I think of halogen light, and so I think of lights.
Well, halogen light also, again, or maybe I shouldn't speak because I don't know too much about it. I'll end up saying something that's not how it happens. Yep. But with free radical reactions, the dangerous part is that once it kickstarts, you can't control it. It has to go. That's why we have to be very strategic. Whenever using free radical halogenation to make alkyl halides, we have to be very strategic and careful in how we design our experiment to get the outcome we want. But anyways, we'll get to that part a bit later. But does everybody see that each of the 4 bullet points are being met here?
Yeah.
Now, imagine you said this, Carrie. What about in when you're actually doing this in a lab? But in a lab, are we working with one molecule? Right, you're taking X mils or X grams of whatever substance. You've got millions of those molecules, and all of those molecules some of them have started this, some of them have started that, and some of them have already reached the termination stage because you've got all of these millions threads going together. So, we are not looking at molecule at a time, we are looking at overall what's going on in that whole system. Yes, Harry?
Does the propagation step sometimes produce energy?
Yes, absolutely.
So then
It can.
That can feed the initiation step, perhaps.
It can. Once this starts, it can come. It can contribute more energy to that. Absolutely. just to elaborate on what Eric says, bond making creates energy, breaking loses energy. So it's really a balance of those two, right? Overall is the propagation stage exothermic or endothermic, and which can obviously have effect on the rest. Absolutely right. Are we good? Termination stage is where molecules go to, or rather radicals go to die. Because this is the stage where radicals used, not created. Radicals used only. Which means bonds created only. Only creation of bonds, no breaking of bonds. So, whatever radicals exist in this whole system, for example, in this example, what I have on the board, maybe a methyl radical, everything is floating around, remember? Maybe a methyl radical came in contact with a chlorine radical, right? I mean, of course, there's an electron, absolutely, they will pair. And what is that creating?
CH3 Cl.
But does this step fall, can it fall under the propagation stage because we made a molecule of the product? No. That step does not fulfill the 4 requirements. So that step, since it's only using the radicals, falls under the termination stage. But can it happen? Absolutely. Because all of these things are happening at the same time. One molecule might be there, but maybe a different molecule has already come here and it's done. It stops right there. We good, everybody? Well, now think about it. Is it possible that one chlorine radical sees another chlorine radical? And the question is, why not? If all of these things are just mixing around and bubbling around in the same container, all of those things are possible. But that equation, that step goes in the termination stage because bonds are being made only. No bonds are being broken. So that step does not fit here, it does not fit here, fits there.
So everything's being used up.
Exactly. Can someone suggest one more termination stage step based on things that are on the board? One more termination stage possibility.
The CH4s?
CH4s. Do you want to say CH4s? You, radical.
Oh.
So,
Methane is not a radical.
can a radical, CH3 radical, react with what?
HCl
But HCl is not a radical.
with another.
With an
Of
H.
itself.
Yeah.
Why not? Can this come in contact with another one of itself?
Yes.
What would that create?
Ethane.
Ethane. Do you guys see that? Can that happen? Absolutely. Here's another funny thing. Can this guy, once it's created, if this is created, even one molecule of that is created in this whole system, can it replace methane in the propagation stage and create a different product? Answer is yes. All of those things are happening and there is no way for us to control it. Those are all possible. However, because I am at the moment writing the mechanism to explain this reaction only, I'm not going to consider it. I'm going to ignore it. But is it happening? I'm sure it is. You good, everybody? Yes?
You said you can't control it. Is that if you like keep all the variables the same, like the heat and everything the same? Like what if you just like turn off the heat or you put it in ice?
Once this has happened, then it's going to go and go and go and go in all possible directions till one of the reactants is used up.
Okay.
That's when the train stops.
Does it matter what changes outside
No.
of that? Okay.
There are some strategic things we can do, which we'll talk about in a bit once we get an idea of the mechanism. But once a free radical reaction goes, you can't stop. Are we all okay with the 3 stages? It's very important when you write mechanisms of free radical halogenation of alkanes that you write them in distinct 3 stages. Here is the initial stage, here's the propagation stage, here's the termination stage. Can I answer any questions? We'll do more. Okay. Now before we write more, Does the product have hydrogens on sp3 hybridized carbon atom?
Mhm.
Yes?
Yeah.
So, is it possible that this reacts again without, again,
Yeah.
we don't have control? None. Does this have hydrogens on an sp3 hybridized carbon?
Yes.
So the
to
point
determine
is-
the chloroform.
The point is, all hydrogens on sp3 hybridized carbon atoms can be halogenated. All hydrogens on sp3 hybridized carbon atoms can be substituted by the halogen radical, and we cannot again control that. There are some strategies which we'll get to later. The point is polyhalogenation. This is called polyhalogenation. Putting more than one halogen on the same molecule is very, very common in these reactions. However, from now onwards, I will never talk about polyhalogenation. Keep in mind, polyhalogenation is always a drawback. It's a limitation, it's a disadvantage of this reaction. But from now on, whenever we talk about halogenation, we will only talk about monohalogenation, only putting one halogen on a molecule. Are we good, everybody? So we are ignoring the possibility of polyhalogenation. So, let's look at one more example, write this mechanism a couple more times, and then slowly get into the, before that. Sorry, before that. Or should we wait? You know what? Let me wait. Okay, let's try this one more time. This time we look at the next bigger alkane. What's the next bigger alkane?
Ethane.
Okay. So how about we brominated this time? I'm just randomly mixing those things. Can someone tell me what would be the product? Again, please note monohalogenated only. We are not going to consider polyhalogenation, even though that is happening. We are ignoring polyhalogenation. So what would be, what would be the product? Anybody?
CH3, CH2 radical plus.
Product.
The
Product is, I know product.
the entire product. CH3, CH2, Br plus HBr.
Do you all agree? Reactant, product. What are the things we call that are created in the middle but then used up again?
Intermediate.
Those are intermediates.
Mm-hmm.
But the overall reaction equation doesn't show intermediates, it shows reactants and products. Do you all agree?
Mm-hmm.
Okay, let's write the mechanism. So, following that same pattern again, initiation stage. What's the initiation stage? The halogen breaks homolytically because of the energy we provided to create halogen radicals. Agreed?
Mm-hmm.
That's our initiation stage. Everybody okay? Bonds being broken, radicals being created. That's it. Then comes propagation stage. Propagation stage is, remember those 4 bullet points that you must make sure are being met. So first step, the halogen that's created, radical, is now reacting with the alkane. Bonds created, radical used, and bond broken, radical created. Has to be important. So what is that creating? It's creating HBr, and it is creating a radical. Agreed? Step 1. Step 2, once that has happened, the radical that is created there reacts with another equivalent. Can I do this, guys? Please tell me. With another radical
Yep.
makes, I know I'm going to get this a lot, so, oops, sorry.
Oh, no.
Let's make sure everybody is paying attention. Is that correct? Is my step 2 right?
Does the radical have to be on the outside?
Eh.
Or, sorry.
Oh, that doesn't, I mean, I've taken my pen and I just, is that what you mean?
Wait, don't we need another, or like the radical?
Does this step fit in propagation stage?
No.
No, it doesn't.
It's only being used.
It's only being used. So
Radicals
where
are
could
being
you write
used.
this step? In the termination stage, you can definitely write this step, but does it fit in the propagation stage? No, it doesn't. Remember the 4 bullet points that are very important for propagation stage. So, absolutely the radical that was created has to react with another equivalent of bromine molecule. Bond created, radical used, bond broken, radical created. So that makes fourth bullet point. You have to show the chain reaction setup. This uses creates, which uses creates, that goes back, creates, and that comes here, it makes it again, it just keeps on and on and on and on. Must do that. Also, what is the sum of these 2 steps? If you add up these 2 steps, does it give us the overall reaction? That's also important, does it? What's the sum of these 2 steps? Anybody? What things can we cancel out when you're adding step 1 and 2? The intermediates.
bromides,
You can cancel these. What else can you cancel?
ethyls.
Ethyl radicals you can cancel. So what's left? You got ethane
Ethane
plus
bromine.
Br2
yields-
makes, isn't that right? Does that match the overall reaction equation?
Yes.
If the answer is no, then something's wrong. We haven't written something correctly. So those 4 bullet points for the propagation stage are extremely important, guys. Initiation stage, bond only broken, radicals only created. Propagation stage, every step has to have a bond breaking and a bond making. Every step must use a radical and create another one. The sum of these steps must equal the overall reaction, otherwise something is not fitting right. And finally, we have to be able to show how this is a chain reaction. We have to be able to demonstrate that, make it visible. Are we good, everybody?
Yes.
And then finally comes the termination stage. Termination stage, as we said earlier, is where radicals come and die, meaning they get quenched. Quenched is a word we use often, meaning you're quenching the reaction. You are completing the reaction. All the reactive entities are being subdued, are being quenched. So radicals, when they combine, bonds broken, created only, fits in the termination stage. Of course, the bromine atoms could also combine and make Br2, but then what else could happen? Which is very common in free radicals. Can 2 of these free radicals come and make butane? The answer is yeah, absolutely. Why not?
Mm-hmm.
So those fit in the termination. Are we good, everybody? Is everyone okay? Questions? Okay, so we'll write more as we go, but please understand, notice the format. It's a very characteristic format of writing these mechanisms. Okay, so let's look at the radical itself before going further. The radical, I'm going to start with the simplest radical that we've seen, the methyl radical. Have we looked at these before, last quarter? I can't tell. Okay, fine. The carbon atom is sp2 hybridized. It's not sp3. It was sp3 before. This carbon atom is sp3, but sp3 becomes sp2 because radical is sp2, and once the next step happens, it becomes sp3 again. So the radical carbon is sp2 hybridized. Do you guys remember sp2 hybridization state? Yeah.
Free electron groups.
So my question is, for the carbon, focus on the carbon, which orbital is the carbon using to make this bond?
A p orbital. Two p orbitals.
Is this sigma? Are these bonds sigma or pi?
Sigma bonds.
What kind of orbitals does an atom use to make sigma bonds? Hybrid orbitals or unhybridized p orbitals? Hybrid orbitals. Always, sigma bonds always use hybrid orbitals. By the way, an sp2 hybridized carbon, how many hybrid orbitals does it have? sp2 hybridized atom, how many hybrid orbitals does it have?
3 orbitals.
3 hybrid orbitals, and what's the shape, angle between them? This is last quarter, guys. One of the things you'll hear me say often, we can't forget what we've learned to learn new things because they're all building on each other. 120, absolutely. What shape would that be?
Trigonal planar.
Trigonal planar. So one of the ways to draw the 3 hybrid orbitals at an angle of 120 degrees from each other if I'm holding it perpendicular to the board. Make sense? So what is this hybrid orbital being used for? In this example, what is this hybrid orbital being used for?
I'm not sure what you're asking.
Yeah, I think, yeah. My brain was also saying something's not quite sounding right there. Okay, without giving up the answer, because I feel like I'll be giving up the answer here. Which orbital on the carbon radical is being used to make the sigma bond pointed right there? The hybrid or the unhybridized P?
The hybrid orbital.
So, what is this hybrid orbital being used for? It is being used for making a sigma bond with the 1s of hydrogen. Isn't that right? Absolutely right? Everybody agrees? So now, what is that hybrid orbital being used for?
Bonding with the other H.
1s of the other H. How about the third hybrid orbital?
The 1s of the other.
So, what's left? If the 3 hybrid orbitals on that 3 radical carbon are being used to make the 3 sigma bonds, what else is on that carbon atom that's not shown yet?
An unhybridized p orbital.
What's the shape of the, or rather orientation of the unhybridized p orbital relative to the plane of the hybrid? It's perpendicular. Isn't that right?
Perpendicular to the
So, where is this electron?
Anywhere within the p orbit.
P orbital. When you say anywhere, like, but in the p orbital. Isn't that right?
Yeah.
Everybody okay?
Yeah.
So carbon-free radical is planar. Its shape is planar. Its shape is trigonal planar. Because the carbon is sp2 hybridized of the radical. We're talking about the radical with the single electron is sp2 hybridized. It's trigonal planar with angles of 120 degrees. And it has an unhybridized p orbital with that single electron. Okay. Everybody okay? Am I late? No. So, we good, everyone? Next question. Would you consider this carbon, the radical carbon, to be electron rich or electron poor?
Electron rich.
Electron rich or electron poor? How many electrons does that carbon want to have? How many does it have?
It has 7.
So is it electron rich or electron poor?
Electron poor.
It's electron poor. Octet rule. It doesn't have an octet. It's 1 electron short. Isn't that right? It's electron poor. Everybody agrees? So a carbon-free radical is trigonal planar. It's sp2 hybridized. The carbon is sp2 hybridized, trigonal planar. It's electron poor. What do we call those entities that are electron poor?
Electrophile.
Nucleophile or electrophile? Can't be both.
Electrophile?
If some ion, it's not an ion, there's no charge on it, it's neutral, so don't call it an ion. But what would it be attracted to if it's electron poor?
Electrons.
Electrophile.
This is a symbol used for electrophile. Doesn't mean it has a positive charge, guys. That plus sign does not mean it's a cation. It just means that it has low electron density. It is electron poor. Are we good, everybody, so far?
E means
Electrophile.
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 Loving electrons.
Yes, exactly. Exactly. Because if I'm electron deficient, then I'm going to go wherever there is more electrons. Absolutely. Are we all okay? So the next question, if that is all correct, then what kind of things, when I say things, I mean atoms or groups attached instead of hydrogen will make that carbon be more stable? If I'm electron poor, what do you need to be for you and I to be good friends?
Electron rich. You have to be rich.
Or if I'm you're right, absolutely. But let's phrase it in a different way.
Need something that can give.
Oh.
Gives electron. If you give me money, you're my best friend, right? Because I don't have money. Same way, the carbon in the center doesn't have enough electron density. So if these guys could push electron density towards the carbon, what would that do to the carbon? Make it happier. Make it more stable. You guys with me?
Yeah.
Everyone okay? So, the order of stability for free radicals, carbon free radicals, we are only focusing on carbon free radicals. Relative stability of carbon free radicals. First and foremost, a vinylic free radical or propargylic free radical or phenyl free radical, absolutely not. These are too unstable for us to ever consider. So, if you're really looking at carbon free radical, the least free radical, stable is the one that has hydrogens on the carbon. Because hydrogens are neither giving nor taking, they're very neutral beings. But then as I start replacing the hydrogens with an R, the stability goes up. Because R's push some of this electron density towards the carbon. R's are said to be electron donating groups through the sigma bond. Not electronegativity though, it's a different kind of an effect which we are not studying, it's called hyperconjugation. But the point is, the bottom line is that R's push electron density towards something else through their sigma bonds. So what is the R doing? If it's pushing some of the electron density towards the carbon, what does that do to the carbon? It makes it less electron poor, so happier. You guys with me? So then what about if I replaced two of the H's with R? And that'll be even more stable, isn't that? And then what would be the even more stable than that? Right? This is a primary free radical because there's only one R on the carbon that has a free radical, two H's, one R. That is secondary free radical, and that is tertiary free radical. And then more stable than that, even more stable than tertiary, can be allylic free radical, just as an example. Allylic, do you guys remember what allylic stands for?
Adjacent
To
a
double bond. So if there's a radical adjacent to a double bond, attached to a double bond, that's allylic. That's way more stable than that. Or benzylic free radical. Does anybody remember what benzylic mean?
Benzene.
Benzylic does not mean benzene. Anybody remembers what benzylic is? Benzylic position is one carbon away from a benzene.
One carbon away from the benzene.
So that's a benzylic position, one carbon from benzene. That's allylic position. They're even more stable. Can someone tell me why? Why is, let me draw it out and then maybe, because I kind of squished everything over there. Fine, a primary free radical is less stable than secondary, which is less stable than tertiary because of the R's, because R's want to give electron density, thereby increasing the stability of the radicals. Okay, done, fine. Which is going to be more stable free radical? Please tell me. Which of these two free radicals will be more stable?
The second one?
Okay, good. Why?
Because it's adjacent to a double
But
bond.
why? Good, yes, but that's the question. So
Um,
let's understand why. By the way, is this primary, secondary, or tertiary? The first one. Is it a primary radical, secondary radical, tertiary radical?
Primary?
Do you all agree? Yes?
Yeah.
There's only one R, and then of course have to be two H's, which are not shown because they are implied. Everybody okay? Is this primary, secondary, tertiary? It's also primary. It's also primary because there are two hydrogens. But it's primary and allylic. So why is allylic more stable than non-allylic? Any reasons? Anybody? Yes?
Could it be
It
resonance?
has to be resonance, the R word, which never leaves us. So can we try and show how? So, what would be the resonance structure? How do you show that resonance? And remember, it's a single electron process, so you have to keep that in mind. You can't have double-headed curved arrows when there's a radical involved. So, what does that do?
Move,
What's the outcome of that? Those two curved arrows. One electron comes from here, one electron comes from here. So what does that create?
A pi bond, but
And
on
then
the
what
other
about the other electron that's in
a
that
point.
bond goes here?
yeah.
So louder?
creates free radical?
Exactly. Do resonance structures exist?
No,
What exists?
The
hybrid.
What
resonance
is the
hybrid.
hybrid of the two?
The single bond, the sigma bond. Yeah.
Right? But where are the electrons?
Would it be represented as a partial positive?
But not positive, no charges here. You can't have charges. It's a neutral entity. There are no anions, no cations. But what you can do, partial,
Partial electrons.
absolutely.
Oh.
It's distributed across the whole. It's distributed across the whole system. Resonance is always extremely stabilizing. If something can undergo resonance, it leads to high amount of stability. Everybody okay?
Yeah.
Yeah? Cool. I'm going to draw some I'm going to draw some radicals. You need to arrange them in increasing order of stability. Increasing order of stability. have four, excuse me, four free radicals here. Let's call them 1, 2, and 3, and 4. Please arrange them in increasing order of stability. So who comes first? Least stable or most stable?
Least stable.
Good. Please tell me which one would that be?
To be
I would think number 1 is less stable. No?
wouldn't it be 2?
Okay, if that's, go ahead, tell me, is this primary, secondary, tertiary? Radical, we are looking at the radical. Is that primary, secondary, tertiary? Are there 2 R's, 1 R, 0 R's,
secondary.
1 R, 2 R, 3 R's?
Second.
Secondary?
Mhm.
Is it allylic or benzylic?
Benzylic. No?
Neither. There's
Oh,
no
okay.
benzene, it can't be benzylic. But it's
I thought it was
also,
one or the other.
allylic has to be the position next to a double bond. It's not. Agreed?
Yeah.
How about this? Is it primary, secondary, tertiary? Primary, is it allylic, benzylic?
No.
It's none. Neither. That's not an allylic position because that's the allylic position. Are you all seeing that? Is this primary, secondary, tertiary?
A little.
That is tertiary.
And is it allylic or benzylic? Or neither?
A little.
It's allylic. Okay. How about the last one? Is it primary, secondary, tertiary? And allylic or benzylic?
Neither.
Neither. Does that help to say which of these is going to be least stable? 2 is least stable, absolutely. What comes next? Number 2? 1,
2, 1, 4, 3.
4. Do you all agree? Everybody says
I'm
that?
just having
Yes.
a little trouble with first one. I see C, 2 H's, and a.
Where? Which one?
Oh, I know. I think I got it. Why was primary? Because.
Because this carbon is connected to 1 R
Okay.
and 2 H's.
Yeah. Okay. Thank you.
Yeah, absolutely. Everybody okay with this? Everyone okay? Questions? Thoughts? Okay, next question then. Now that you understand the basic idea of the free radical halogenation of alkanes and a little bit about the free radicals themselves,
May I ask you
Yes,
before
please.
that? What would you call that one if
methyl.
not?
That's
Just
a good
methyl.
question. Yeah, you just call it methyl because there's no other term you can really give it. It's a methyl radical.
Methyl radical.
Yeah.
Okay.
Methyl radical, primary radical, secondary radical, so on and so forth.
No, thank you.
Yeah, absolutely. Okay, let's do this next. Let's go to the next alkane. Propane. Let's say we are brominating propane, meaning that I am reacting propane with bromine and this time I'm heating it. Can you tell me how many, and I'm not interested, okay fine, tell me the products.
Propyl bromide plus hydrobromic acid.
Is that it? So I heard propyl bromide, I'm assuming you mean 1 bromopropane,
Yep.
and HBr, is that it? So, let's pause. We've done NMR, right? Last quarter we did proton NMR. When you look at propane, how many proton signals do you expect? How many types of hydrogens does this molecule have? 2. What are those 2? It has 3 here.
The
that are
methyls on
equivalent.
each.
What about those 3? Are those equivalent to these 3?
Yes.
Absolutely. And what's the second kind?
The 2 hydrogens.
There are 2 kinds of hydrogens, agreed? Then there should be 2 alkyl halides. If one of the red hydrogens was substituted, you get 1 bromopropane, agreed? What if one of the blue hydrogens was substituted, what would we get? 2 bromopropane. Isn't that right? What's the relationship between these two products? By the way, from now on, please understand us chemists are very lazy about byproducts. HBr, who cares? Fine, it's there. We are really interested in these guys. So if I forget about that guy, don't think that I don't like it. It's just that
But like,
it's not very consequential. The point is we are focusing on the organic product. But do you agree there are two organic products? Is everybody in agreement? Can you tell me what's the relationship between those two?
Isomers,
They are
structural.
structural isomers. Absolutely, they are structural isomers. There's another term we use for structural isomers. Can someone tell me what are the other terms we use for structural isomers?
constitution?
And one more?
Uh,
Starts with R.
Regio.
Regioisomers. Now I want to use that
What?
term only. This is called regioselectivity. Guys, I'm going to introduce some terms that will become part of our vocabulary. One of the things we discuss in a lot of these mechanisms is there regioselectivity? Please notice how the word is regioselectivity. What does that mean? Any guesses?
One is preferred over the other.
Exactly. But when you say one, let's be more specific about that, Eric. When you're saying one, what is the one you're referring to?
One of the isomers.
Exactly. Which isomer? One of the regioisomers. Because very soon we'll talk about stereoisomers. And then you got to become real. So the point is, when we discuss mechanisms, oftentimes we've got to discuss, is the reaction selective towards one regioisomer? Please remember the word regioisomer means structural isomer. Over the others. Or is it not? In some cases it's not, but in this case there is regioselectivity, meaning selectively the reaction creates one of them in more quantities than the other. Do we understand the term?
Yes.
Okay, so now let's look at this reaction. I will ask you to do this at home, guys. Practice writing this mechanism. It's all about practice. It's all that muscle memory that we've talked about often last quarter. Please write complete mechanism for this reaction and for this reaction. They'll be separate mechanisms. So show mechanistically how one bromopropane can be made and show mechanistically how two bromopropane can be made. Same thing, initiation, propagation, termination stages. Carrie, did you have a question?
More thought process, I think.
Okay, so let's think together.
So like regioisomers, like region, like which
Exactly.
location that the brom.
Exactly. Does it go here or does it go exactly? That's where the term regio comes from. Exactly. You guys with me? Now I'm not writing the mechanism, which I'm hoping you guys will do at home to get practice. What I want from you though is, can you tell me how many free radicals? Let me say that. Can you tell me how many alkyl free radicals can we create from propane when you write the mechanism? Okay, fine. Let me ask the same question differently. Can you, 8? No, not 8. Because then there should be 8 products. Every free radical creating a product, which is not the case, right? Okay, can you tell me what will be the structure of the free radical that leads to the formation of one bromopropane? Where does the radical have to be if you think about the mechanism in order for us to get that product? Okay, do you agree?
Yeah, that's what it is.
That's all I'm asking.
Oh.
Exactly,
The
that's all I'm
propane-
I thought you were
propane
asking like
minus the
where did it
hydrogen.
go
No,
after?
no. Keep it simple. But do you agree?
Yes.
I'm not writing the mechanism here, I'm just discussing the sequence of
Free
events.
radicals.
So can you tell me what would be the radical that creates the other product, 2-bromopropane?
The second carbon minus the
Secondary
hydrogen.
radical, right? Which of the free radicals? By the way, is this primary, secondary, tertiary, allylic, benzoic, what?
Primary.
Right? How about this guy?
Secondary.
Okay, so which free radical intermediate is more stable?
The primary.
The one at carbon 2.
Do you agree? Everyone okay? So please think about this and tell me. If I have two paths I can go in, and this is easier because it goes through a more stable intermediate, which path will I go more towards?
Stable.
There you go. That is the regioselectivity here. In this example, that will be the major product, meaning created in greater quantities, because it's coming from a more stable intermediate. The regioselectivity in the free radical halogenation reaction is that the more stable free radical intermediate creates the major product. Now, what do I mean by major product? What I mean by major product is if you had both of them will be created, but there'll be more of this, less of it. That's all it means. We good, everybody? Yes.
Okay, so I get it, but I notice there are two sides to that molecule.
Right, but aren't they equivalent?
So in other words, my thinking, there's two opportunities to do the less
Oh,
stable one.
good point.
But
Statistically
there's only
versus.
one opportunity
Very
to do the
cool.
more stable one. So does that like balance
Yes.
out and such?
In this reaction, that's actually important. What Eric is talking about is there are 6 of those, right? But there are only 2 of those. Statistically speaking, which product is more favored? Statistically speaking, which hydrogen will get replaced more of?
The tertiary.
The
That's right,
more
the
primary.
The primary
Because there are more
ones.
of. Whereas compared to this, so that is a statistical outcome, which is what we see in fluorination, because it goes so fast, it doesn't give the reaction time to calm down and look at thermodynamics. Thermodynamically speaking, though, it goes towards the more stable radical. So fluorination is so fast, its rate of reaction is so high that yeah, it will give us that as the major product, no doubt. But it's also so exothermic that practically speaking we do not use it. So I'm not talking about chlorination. But in terms of chlorination and bromination, their rates of reactions are slow enough that it gives the opportunity to the molecule to, okay, calm down. Yeah, there are 6 of those, 2 of us, but we are stronger because we can create more stable radical compared to those. So the rate of the reaction allows us to therefore get that regioselectivity. You're absolutely right. Statistically speaking, things will change. So, but again, I don't want to talk about that more because fluorination we will not discuss. Iodination we will not discuss. We will only discuss chlorination and bromination. So, major product, at least for these 2 pathways, will come from the more stable radical. You guys with me? Everybody okay? Cool. I do want to mention one other thing before we leave, which will also address what you are referring to, Eric. I'm going to use the same for now. Chlorination versus bromination. Reacting with chlorine versus reacting with bromine. Now, reacting with chlorine is faster. The rate of reaction, the kinetics, is faster than bromination. And because of that, we see exactly what you said earlier, Eric. We still do see the major product coming from the more stable radical. However, the distribution is much lower in chlorination versus bromination. That's because of the rate of the reaction. Chlorination is faster than bromination, that it doesn't allow the flexibility for the molecule to actually choose the more favored path. It just go bam, 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 done. And that's why, yeah, fine, that's still the major product, but notice the distribution is way different. So most of the times when we want to get the more stable product, bromination is way better than chlorination because we get a much higher percent yield of the favored product over the less favored product and chlorination. But again, for me, for us, for at this stage of the course, either is okay as long as you understand the regioselectivity for this reaction is that the major product comes from the more stable free radical. Are you guys with me? Okay, let's stop here. Please do write the mechanisms, full mechanisms, initiation, propagation, termination, explaining both of those products. We'll continue from here to Wednesday.